Okay, I think it's start now. So hello everyone, welcome to the Exit demo session, mobile application. I am Eileen Low from Purdue University, and I'm very happy here to be the session chair today. In this session, we're gonna have 3 papers to present. And for each paper, we have 15 minutes, including 5 minutes presentation, followed by 5 minutes demonstration, and lastly, a 5 minutes Q&A. So the audience, please feel free to type any of your questions in the chat box. And the authors of other papers, you are also encouraged to ask the questions of the current speaker. So let's start our first paper. Our first speaker, Tarek from Texas State University. The paper title is an ACID, an API compatibility issue detector for Android app. So maybe Tarek, you can start now if you're ready.
Thank you. Can you see my screen?
Yeah.
Hello everyone, I am Tarek Mahmoud, a PhD student from Texas State University. Today I am here to present our demonstration paper on ACID, an API compatibility issue detector for Android apps. This is a joint work between Dr. Che from Data 621 CSIRO and my advisor Dr. Yang from the University of Queensland. So Android is the most widely used mobile operating system. It is frequently updated to accommodate the new feature requests, meet new standards or bug fixes from previous versions. Android apps are developed using a software development kit where the APIs enables app developers to use the functionalities of Android devices by interacting with services and hardware. APIs have also evolved along with the Android OS. In the last 13 years, Android releases a total of 11 OS updates and 30 API updates. This shows how frequently the Android OS and API are evolving. Android app developers have limited control on devices where their apps will run. Google recommends that developers to specify the range of the API levels their app can support by setting min SDK version and max SDK version. The mismatch between the API level supported by the device where the app is running and the API level targeted by app developers can induce compatibility issues. And API invocation compatibility issues occur when an app invokes API methods that are not supported by the device API level. And the API callback compatibility issues occur when overridden API methods are invoked in response to an event but are missing in the API level of the device. Here is the overview of the framework of ACID. It takes the app code and the API difference report as input and outputs potential API invocation and callback compatibility issues. ACID consists of 4 major components. The first one is API difference analyzer. ACID leverages the API differences report to find out all changes involved in an API update. Whenever a new level of Android API is released, Google releases an API differences report summarizing the changes between 2 API level specifications, 2 consecutive API level specifications. These API difference reports consist of added, removed, and changed methods. ACID parses the differences of all the API levels between min SDK version and max SDK version. This allows it to determine which method invocations and callback can potentially induce compatibility issues in each API level within the API range that is supported by the app. API difference report does not consider the differences between non-adjacent versions. It is only for the consecutive versions. So ACID accumulates all the changes compared to the target SDK version of the app. We name those methods suspicious API methods as they can cause compatibility issues. API usage locator takes the app code as input and outputs all API invocation and callback usages within the app. To collect API invocation usages, it searches the API method invocations using a self-built miniature lexer and parser for Android source code. Then it applies a backward data flow analysis from the API usages to extract the types of the parameters used in the method invocation and the return type of the methods. To collect the API callback usages, it generates the class hierarchies to find if any class extends API classes and overrides API methods. For both cases, ACID checks if the API usage is under any API level conditions or not, which is also called the guard conditions, which are used to address the compatibility issue. API invocation compatibility issue detector uses the API invocation usages in the source code generated by the API usage locator and the suspicious API methods generated by the API difference analyzer. API callback compatibility issue detector detects compatibility issues by checking if any overridden API method is final or identified as suspicious by the API difference analyzer. We used 20 benchmark apps from the previous studies, 7 benchmark apps that were previously used to evaluate CID, which is a API invocation compatibility issue detector. And we also took 13 that were previously used to evaluate CIDR, which is a callback compatibility issue detector. We compared ACID with CID and LINT to verify the accuracy of ACID in detecting invocation compatibility issues. The table shows the experimental results. Comparing all the results, we can see that ACID outperforms the other 2 techniques in detecting API invocation compatibility issues. We conduct experiments on the CIDR benchmark apps and compare the results of ACID with CIDR and LINT. As shown in the table, ACID detected 36 compatibility callback compatibility issues, while CIDR only detected 9 of them. The reason behind CIDR's underperformance is that it only considers 4 classes that were manually modeled. ACID is publicly available on GitHub, which has detailed information about how to download, install requirements, and run ACID. Let's move to the demo section of this presentation. I just close this.
Tarek, I think you are going to share a demonstration, right? Great.
Yeah. Can you show the screen?
Yeah, perfect.
Okay. So in this demo, we use an example app to illustrate how to use ACID for detecting compatibility issues in an Android app. First, you need to clone the repository from the GitHub. There is the README file that has the detailed information about how to actually install requirements and run ACID. The prerequisites for running the tool are Python 3.8, Java version 8, Boost Graph library, and GraphViz. And the other Python requirements, Python library requirements are mentioned in this requirements.txt file. You will be able to install them using this command, pip install -r requirements.txt. We use the source code of launch time for this this example. First, we clone the repository of the launch time application in this example folder. Within the app, we first identify the folder where the app code is localized. So within this launch time, we found the app code is under app source main and then Java. This com.coop.launch time is actually the package name. So if there are multiple packages, they all will go under this Java folder. So as the app code, we take the app/source/main/Java. So we only consider this folder for analysis because there might be other Java files like JUnit tests or automated tests, which should not be considered for detecting compatibility issues, as they will not be the part of the application when the app will be released to the users. Using this path, we can run ACID using this command, Python, then the file name, and then the path. If we run this, it first collects the API differences for all the supported APIs. If the API differences are available in this API versions folder, ACID accumulates the suspicious API from them. Otherwise, it collects the differences from the API differences report website and saves them in this folder for future usages. In this case, we already have them, so it doesn't download anything new. Then the API usage locator locates all the API usages, both invocation and callback API usages. Finally, the compatibility issues detector detect the compatibility issues. the output is by default saved in this compatibility issues.txt file. If we open this compatibility issues.txt file, we can see two types of compatibility issues are there: API callback compatibility issues and API invocation compatibility issues. Here for this app, ACID detects two API callback compatibility issues and 3 API invocation compatibility issues. For each compatibility issues, ACID reports the incompatible API, which API from Android SDK is incompatible, and the usage in the app code, and the incompatible API levels. If it shows less or equal, then it means the backward compatible. It has backward compatibility issue. If it shows greater or equal, it is a forward compatibility issue. So using this information, developers can easily debug the compatibility issue in the source code. Like if we follow this path, like for under this package, if we can find this pin shortcut activity folder, like under this package, there is a file called pin shortcut activity, and in there we can find the incompatible API usage in this onCreate method. So onCreate method here is the incompatible API usage, the get system service. So that's all for my presentation. Thank you for your attention. If you have any questions, please feel free to ask.
Thank you, Tarek, for this talk and demonstration. And there is any questions for Tarek about his work and demonstration? Or you can type your question in the chat box. I can first ask my questions. So
Yes,
Tarek, so I think your tool is quite very interesting and also with a high effectiveness compared to some existing tools. Just quite curious about the one false negative case that your tool cannot accurately detect. So what's the potential reason and the condition for that case?
can you just repeat the question?
Yeah, well, I think there is a false negative case. I think some cases cannot be accurately detected by your tool in your slides just shared.
Yeah, because we worked with for some cases it creates false positive and false negative, as we used the tool suite for backward data flow analysis, and for Java's reflection and other cases, for Java it reports some false positive and false negatives.
Okay, so it's possible the toolkit you used in your to implement your tool. That what do you mean?
Yeah, for that case, we actually missed some cases, and also if you consider the dynamically generated files, we worked with source code. Here, the source code doesn't contain any dynamically generated files. So if there is any compatibility issues in the dynamically generated files, it will miss them. If we work with the DEX files, which also our tool works on the DEX files, the decompiled APK files, so there it can it can detect the dynamically generated compatibility issues too.
Okay, I think. Thank you for the answer. So is there any ask question for Tarek? Oh, I see. I saw there is a question in the chat box, and Secretary, you can see it as well, right? It's from Lin Xiaojiang. It says that Sanks looks have some different and similar features like Android Involve and ICPC20. So how is ACID different compared to this work? So maybe you can ask questions.
Which one? I can see it. Oh, in the chat.
Yeah, it's in the chat box.
Android Evolve actually works on updating the what did it say? Updating the deprecated APIs. So they first, I have gone through that. They actually first normalize the target app code. Then using the examples, they actually normalize both the target code and the example code, and using that normalized example, they update the target code and denormalize them. They use the data flow analysis to find those methods that we also find the API, not API usages, find the variables usages over the class structure. Out of bound method, they actually out of method bound variables, get those using the data flow analysis. That is the similar thing we do in ACID, but the basic things are totally different. The basic purpose of the Android Evolve and ours is totally different.
Yeah, I see there is a focus
Yeah, I guess so. Using ACID, you can detect compatibility issues, and then you can use Android Evolve to update that compatibility issue.
Yes, so maybe you can continue to discussion or question offline. So we can thanks again for the presentation and the Q&A. So we can move to our next paper. Our second speaker, Jiwei Yan from Institution of Software and Chinese Academia Sciences. And the paper title is Fragment-Aware and Context-Sensitive ICC Resolution and Android Applications. So Jiwei, maybe you can start if you're ready now.
Okay, thanks. Okay, hello everyone. This is Jiwei Yan from Institute of Software, Chinese Academy of Sciences. Today, I'm glad to share with you our recent work, which is a fragment-aware and context-sensitive ICC resolution tool for Android applications. First is a brief introduction of Android components and the ICC mechanism. Components as essential building blocks of Android apps. One Android app usually have multiple components, and each component can be taken as an entry point of the app. Actually, these components are not isolated. Instead, they can activate others or just communicate with others by sending the intercomponent communication messages, short for ICC messages. By resolving these ICC messages, we can see the transitions among components. This structure is widely used in many application scenarios, including the GUI structure understanding, the safety property checking, and test sequence generation. Then let's see the process of ICC message sending. An ICC message usually has a source component and a target component. First, the source component will create an intent object and send it to the framework. Along with this intent object, both the basic ICC fields like the action category or the user customized extra data will be delivered together. Then the framework will receive and resolve this intent object. After that, it will determine the target component to be launched. In this process, one key point is how to obtain the data value of the ICC fields precisely. In some scenarios, this data will be transferred among multiple methods, and so that the analysis of the calling context is important. And another point is the usage of the fragment. A fragment is an inner component which is hosted by an activity or another fragment for the reusable user interface. In this example, we can see the source component first sends a fragment loading statement and launch the fragment. Then the fragment will send the ICC, send the intent object to the framework, and then framework resolve this intent and launch the target components. As fragment is widely used in recent days, I think it is important to resolve the fragment loading statements and extract the ICCs that connected by extract the ICCs connected by these fragments. In our tool ICC bot, we consider the two characteristics: the fragment loading and context-sensitive data value tracking, specifically to improve the completeness of the constructed component transition graph. This is a high-level overview of our tool, which contains 4 modules. First is the control flow analysis, focus on the construction of the dummy main method, the callback methods, the call graph edges. The data flow analysis focus on the interprocedural context-sensitive data value tracking. And the object module focus on two models, the intent model and the fragment model. And finally, the summary construction part will build summaries for each level, for example, the method and object and the path. In our tool, the default client is the CTJ client. It takes the APK file at input and outputs the constructed component transition graph. This is the user interface of our tool. It displays the multiple parameters provided to users. Users can set them to adjust the tool. And it also provides several analysis clients to users. Users can use them directly or just build their own clients upon them. Then let's see an example of the fragment loading graph. In this graph, the red nodes are the activities and the green one are the fragments. And this is an example of the same application. It's the component transition graph. As we can see, it is more complex and there are many fragment nodes involved. To evaluate the effectiveness of our tool, we compare it with 3 state-of-the-art ICC resolution tools. Here is the result on the handmade benchmarks. And this is the result on 2,000 of open source F-Droid apps. As we can see, ICCBot can identify more ICCs than others. And the 2 strategies of our tool can help to identify 8% and 25% of ICC edges. Okay, next I will show a quick demonstration. Okay, to use ICCBot, first we clone the project from GitHub. It may take several minutes. And then let's see the README file. It displays how can we use the parameters we provided. For example, the time and the characteristics we want to include or exclude. This interface provides the 6 basic clients we provided to users. Then we build the project to use the given script. This is very quickly. After that, we will run the app to analyze a small application, a benchmark app called ICCBot Bench, which is designed specifically with several ICC message usage. Okay, it finished. And then let's see the generated result. Here are 4 folders. It reflects the 4 analysis clients it invoked. First, the manifest-related information is displayed in the manifest info folder. This client can be invoked directly, and our enhanced call graph information is displayed in the call graph info folder. The next one is the fragment related information. We can get both the graphical fragment loading graph and other detailed information about each fragment loading edge. This is the fragment loading graph for this simple app. It contains only 3 fragment loading edges. And this folder displays the result for the constructed component transition graph. This is the component transition graph without the fragment nodes. And in this graph, we display all the fragment nodes in the graph. Besides, we can also get all the detailed information of each ICC edge in the other fields, including their data value of each ICC fields and the method trace to reach intent sending statement. This is a very simple app. Then let's quickly see another real-world app. We just see the result of the fragment loading graph and the component transition graph. This is the fragment loading graph for this app. As we can see in this fragment loading graph, we consider both the edges from activity to fragments and from fragments to fragments. The other edges are not included in this graph. And this is the result for the component transition graph without the fragment node. And that one is the result with fragment node. Okay, that's the demonstration. In summary, this paper presents the fragment-aware and context-sensitive resolution tool for Android apps. It can efficiently construct a component transition graph with a higher accuracy. It also generates friendly outputs to users. Our tool now is public available on GitHub. Users can also scan the QR code to visit the project directly. Also can contact with me with that email. Okay, thanks. That's all.
Thank you, Jiwei, for the nice talk and demonstration. So if the audience or the other authors have any questions, please feel free to type your questions directly in the chat box. Or maybe I have missed something, so I'm just curious, how was the overheads of your tools?
The overheads.
Yeah, I mean the time cost.
Oh, yeah, about efficiency, I didn't give the details. There is a result of the efficiency of our tool on the 2000 open source apps. On average, the analysis time on these open source apps are less than 1 minute. We also try to use the tool on the real world apps downloaded from the Google Play. The time may be a bit longer, maybe several seconds, maybe several minutes, or even half an hour on some complex apps. To cope with this problem, we allow users to set the upper time limit of the analysis, or just adjust the maximum number of passes analyzed in a method, so that users can control the analysis time according to their requirements. Yeah, for most apps, it's on the real world apps, the analysis time is usually several minutes, I think. But for complex ones, it may be longer.
Thank you for the answering. So I saw that Mulin has posted a question in the chat box. Maybe Jiwei, can you see that chat box? And I think we have two questions. Maybe first the Mulin questions. He is asking the classifications impact on the analysis results of your tool. Would you please answer these questions first?
I can't see the question. Can you repeat it for me? Thanks.
You cannot see in the chat box.
Oh, I can't see.
Maybe I can resend it from. Can you see it now?
No, I still can't see it.
Well, okay, maybe Mulin, you can ask questions from your own since you are already in the room. Maybe you can directly discussion, right?
Yeah, thanks, Jiwei. Actually, I mean, so you know, some applications may choose to obfuscate their code during the compilation. So my question is just wondering that will the obfuscation have an impact on the final analysis result of your tool?
Okay. Can you say it again? Sorry.
Will the obfuscation have an impact on the analysis result?
I think it doesn't influence our tool because we just concentrate on the specific API, which is not obfuscated.
Okay, thank you.
We don't concentrate on other user defined methods. We don't concentrate on their name. Yeah,
that makes sense. Thank you.
Yes.
Well, we actually have a second question from Lin Xiaojiang for you, Jiwei. He asked that thanks for the demonstration, the ICC resolution tool for 2,000 open source apps, how to access the precision of the resolution results.
The precision.
Yeah.
In our evaluation, there are two parts. We first evaluate on 3 handmade benchmarks with the ground truth, so we can know the true positive and the false positive. And on the real-world apps, we do not have ground truth, so we just compare the number of ICCs. Although the number of ICCs is not very precise to evaluate the tool because there may be false positives and false negatives. According to our manual review, there are some reasons to raise the false positives or false negatives of our tool. I can give a brief introduction. For example, the callback entry identification is the one main reason to cause the false negatives, because if it is in process, we can have trouble to recognize the control flow. Other reasons, for example, the modeling of the containers, for example, the adapter, it influences the data value tracking of the ICC fields. And for the false positives, I think our tool have one strategy. We use the top methods from that we can extract it from the call graph to be the entry method of the ICC message if the top method located in a component. However, sometimes we can't know whether this top method is really an entry method or not according to our entry method identification approach. So that may raise some false positives.
So I think it's a follow-up confirmation that it's a manually an analysis of the samples of our real-world apps, right?
Yeah.
Okay, cool. Well, thanks again for the presentation and the demonstration. So maybe we can move to our last paper. And our last speaker, Mu-Ling Duan from Singapore Management University. The paper title is Unrooted Dynamic Monitor for Android Apps UIs for Fine-Grained Permission Control. So Mu-Ling, feel free to start if you're ready now.
Yeah, thanks, Yiling. Can you see my slides now?
Yeah, we can see it.
Okay, cool. So hello everyone. I'm Mu-Ling. I'm glad to be here to present our work UIP Joy for you. So today, while user enjoys the convenience brought by the smartphones and third-party applications, they should also have to bear the threats like data leakage. So to help the user to protect their privacy, Google provides a runtime permission mechanism as well as a permission manager to allow user to control their permissions. Okay. However, we argue that the current permission management mechanism is too coarse to protect users' privacy. Because once the user chooses allow some application to access their privacy, the application can permanently get the access to users' privacy, and system will not notify user about the subsequent permission usage. And also for permission requests, user only have limited option, namely allow and deny. So sometimes if user refuse to grant permissions to third-party applications, they may even cannot use the basic functionality of that applications. And finally, the current permission management system is a lack of a report telling user which permission is used by who and when. Okay, so these are the key motivation of this work. So based on the issues we just talked about, here are some key features and also the design goal of our application. So firstly, unlike the existing works, to allow more users to use our application, this solution is totally useless. And secondly, our application is able to distinguish between the different context of the permission request. And we will talk about more about the definition of this context in the demo session. And finally, our tool provides enhance the user's awareness of a permission usage through like toast message and permission reports. Okay, so let's quickly have an overview of the architecture of the whole work. So firstly, user should install the applications that they want to monitor on a framework named Virtual Expose. So that's why we call them virtualized application. Instead of allowing virtualized applications directly access the sensitive APIs to get the user's privacy, our hooks will first intercept these sensitive API calls, and then hooks will check with our customized permission manager to see whether these applications are allowed to do so. Then the permission manager will check the decision database to check the user's existing decisions. If it cannot find the existing decision, it will push a notification to the user and ask for their decisions. And all the existing decisions will be displayed on the permission configuration UI. So once permission manager gets a result, right, it will return this result to the hooks. For example, user's existing decision maybe want to return a fake value to the virtualized applications. So the hooks will modify the data it gets from the sensitive API and return a fake value to the virtualized application. Okay, so here is an overview architecture of our tool. Now, why don't we have a quick demo and come back to this slides again. Let me quit the presentation. Just want to make sure that, can you see my Android phone screen?
Yeah.
Okay, cool. So firstly, like I mentioned, we should install the application on the virtualized framework named Virtual Expose. So this is a Virtual Expose. I have already installed the 2 applications on here, as well as our tool UIP Joy. So today I want to show you 2 scenarios. The first scenario is that for some instant messaging and social media applications, you can add friends or build connections by allowing application to read your contacts, and they can tell you which of your contacts are also using this application. Then you can add your contacts. So here I use a self-made application to simulate this scenario. So for example, once you click add friend, right? The application will ask for your permission. And here, for example, we will choose allow to allow them read my contact, and okay, and also allow them to manage my course. Okay, and you can see once I click allow, the application can read my contacts. So here I also display the reading result on a list view for your convenience. But wait, if we click allow, other UI widgets, for example, you can see there is another button on the screen, and also some system background, the application background service can also read our contacts, right? And the system will not notify about the subsequent permission usage anymore. So for example, if I click another button, right, it can also read my contacts. So which is a very dangerous and very quite annoying, right? So what should we do here is let's go back here and open our tool UIP Joy. Yeah, and see this permission request application. Let's choose to return fake value to it. Okay. Then we also have to enable our UIP Joy. So it's quite easy. Check the checkbox. Then we just need to reboot our phone. Okay. So that's that. Let's go back to the permission request application again. Now, if we click any button of this application, so as you can see, here are some dummy value, right? It cannot read my real contacts anymore. All of these characters are randomly generalized, so which can help us to protect our privacy. Okay, so this is a very simple scenario. Then let's go back and temporarily disable our tool. Let's come to the scenario 2, which is a little bit complicated. It's a map application. This map application is my favorite application when I was in Singapore. So, sometimes when I use an application, I may just want to browse the map, or I may just want to search a specific location. For example, I just want to know where is Singapore Management University, but I don't want to go there, which means that I won't use the navigation functionality. So in this case, it doesn't make sense that to allow you the map to get our location, right? Because app map always periodically scan our current location and displays the current location on the map, right? So here, when we first execute this application, it will ask for our permission, right? So here we choose allow them to access my location during the runtime. Okay, and let's zoom out because the network is maybe not good. Okay, I think you can see this is my real location. Currently, I'm based in Shanghai, so it's successfully get my real location. So what should I do if I don't want the map to get my real location? So similarly, you can open the UIP join, open the selection for the Singapore map, this application, and then you can choose a return fig value, choose the access course location, and the return fig value when it try to access your fine grained location. Yeah, that's all. So similarly, reboot your phone. Yeah. So that's all the setting you have to do. Then you go back, restart the Singapore map, this application again. Yeah, let's maybe we should wait 3 seconds. Close the advertisement. Maybe due to the network issue, because currently I'm based in China and the network to access the application server is not good. It cannot show up on the application, but ideally here should be display a fake location. It will say currently, it will say currently I'm in Singapore, like this. Okay, so due to the time constraint time, we won't wait this, and we won't wait for the result. Let's go ahead. So another example is that what should I do if I want to use the navigation functionality, or what should I do if I just want to say where am I, right? So in this case, usually I will click a arrow button on the map, right? So you can see the arrow button is on the left-hand side of the screen, which is above the zoom in button. So in this case, what should we do? Should we go back to the UIP join and change the setting to allow for this application? Actually, no, we don't need to do so, because a switch between the allow and the fake is a little bit not inconvenient. Is inconvenient, right? So what can we do here is open the UIP join again, and let me import a config file. Import a config file. Okay, it's successful. Then I will switch to the button hook setting. So you can see, and there's a Singapore map, access fine location following by a number, which is the button ID, which is the ID of that button. So here we choose a allow, which means that we trust this button, and every time when I click this button, we hope the application to get my real location information. Yeah, but please notice that once you click the button, it will get your real location. But the system service, like the background service, will still get your fake location. Okay, so that's all the setting you have to do. Then let's see, does the network get better now? Reboot the phone, reopen the Singapore map. Okay, close the advertisement. All right, so seems like with no luck, it can still not refresh my fake location and real location. Okay, so don't mind, you can see the successful event on the demo video of this tool. Now let's quickly go back to our slides and see the conclusion part of this work. Okay, so let me summarize the work. So basically, this work provide a fine-grained permission management system and does not need the user to root their phone. And secondly, we allow user to return fake value to the application, and their using experience will not be affected. And lastly, we provide a permission user report to enhance the user's awareness of their data privacy usage. Okay, I think that's all for the presentation and demo. So thank you, and let's see whether you have any questions. Yeah.
Thank you, Molin, for nice talk and excellent demonstration. So if you have any questions, feel free to ask in the chat box. Well, maybe I can still take the privilege of as a session chair to ask my small questions.
Yes, please.
Actually, I'm not an expert here, but as a user, I'm just curious that for the current UIP job, does it support all the kinds of apps?
Unfortunately, according to the experiment we did, the answer is no. Because, like I mentioned, the first step of using the UIP join is that you should install the applications that you want to monitor onto a framework named Virtuax Post. However, during the experiment of this work, we found that some application cannot be installed on this framework, which play like a container role. Okay, so which means that we cannot install all the applications on this container. For example, you may see this on the paper of our work, right? So we have a column named Virtuax Post loaded. So if it is marked as N, which means negative, for example, Facebook, we cannot install the Facebook on the Virtuax Post, which means that our tool cannot application. So, but I want to emphasize that this is not because of the UIP join. This is a framework issue, right? Okay. I think, yeah. I hope this answers your question.
Yeah. Thanks for the question. So do you have any future plan for addressing such a limitation for the implementation?
Yeah, so the framework is one of the most important question that we are trying to resolve in the future work. We hope to make it support more and more application, because current the rate of the supported application is not very good. So this is most important question we are trying to resolve in the future. Yeah.
Okay, I think the other author Ling Xiao has also shared some tools and a link in the chat box. If you are interested, feel free to check out. Yes, is there any questions for Ling?
I have a small
Where?
question.
Yeah, Jiwei, you speak. Yeah. Please go ahead.
I want to know how to generate the proper fake data for all kinds of permissions. Does the UIP Droid generate one data for all the apps for one permission, or generate the fake data for each app specifically?
Actually, we generate a fake value. For example, if you have two applications, and both of them will read your contacts, right? And so my answer is for these two applications, they will get same fake data. Yeah. And similarly, if you have two maps, Google Map and another map, if they trying to get your location data, they will find you are at the same place. So the answer is the fake value is the same. Yeah.
Okay, can users set this value by themselves, or it is just randomly generated by this tool?
It's a randomly generated. Yeah, because it's not very difficult because, for example, for the context, right? For the context, we just need to use the randomize the character to replace the name and phone number, which is a number, right? So, and similarly for the location, in the background of the Android system, location is a float number, right? So we just need to modify that float number. So that's how we generate the fake value. Yeah.
Yeah, okay, thanks.
Yeah, thanks, Jiwei.
Well, since we're almost run out of the time, maybe we can just close the session. Thanks again for attending and discussion in this session, and thank you. Bye.
Thanks, bye.
Yeah, thanks, Yiling.